Recording. Okay, so welcome everybody. Welcome to Biostatistics and Informatics, BTM6000. So this is a course we're doing now since 4 semesters already. And I think this is a wonderful course and a wonderful opportunity to essentially give you exposure to data analysis, statistics, epidemiology to some smaller degree, also some exposure to public health methods, as well as interpretation of analyses. And I think this is something that will be important for you in the realm of biotechnology management, because I have a very strong opinion that statistics are something that are very omnipresent in our lives. In some shape or form. Big data is something that takes over our lives. Hi, Giovanni. Thanks for joining. Big data is taking over our lives, and all things that you hear in your daily life, be it machine learning, artificial intelligence, all of these methods essentially are methods that base on the same statistical principle that we will be discussing in this class. So I am 100% convinced that these fundamentals of statistics are actually very central to whatever more sophisticated applications you will be encountering in your life. So you have seen my introduction, and I encourage you to please also introduce yourself. I really want to see where you are, what studies you're pursuing, what you're currently doing, and what your backgrounds are, what your exposure to statistics was. I'm looking forward to learn more about you as well. And so as you have heard, I have somewhat an unconventional career. So I studied medicine back in Austria. I went then from medicine directly into research, commenced a research career, did a PhD then in medical science, and went from there in the realm of epidemiology and biostatistics. And I followed my passion. I really, truly followed my passion, and I feel very happy with what I'm doing right now. And now, as an additional mainstay of my professional life, I have embraced now teaching, and I do truly enjoy teaching. So I'm here really for passion, and I really want to pass on knowledge. So please never hold back. If you have questions, if you want to dig deeper into any topic, please absolutely don't hold back. Ask me questions. Let's dig deeper. Let's see what I can help you with, or what resources I can guide you to, and how I can help you to understand the subject matter in more detail. And so really be open-minded. Some of you may do data analysis down the road. So I have had students who were very interested in doing data analysis and pursuing a career in data analytics. Others of you may not, and that's perfectly fine as well. But I think having some exposure to the backgrounds and what data analytics is all about and what statistics is all about, including the ability of programming some basic R, is something that it will open your minds to some extent. It will open your minds to what you can do with analytics, what an analyst or a statistician that will do analysis for you has to undergo, the process he or she will undergo, what information he or she will need, and how you can make the life of your analyst or your statistician easier, and how you actually support him to provide an accurate and efficient workflow. So all this being said, so we will be starting to talk today about data sampling and the design of experiments. And this is really where everything starts. So you need to understand what data actually is. When somebody talks about big data, what is big data, right? Like nobody really may not have seen what big data actually entails and how that actually looks like. So there are various ways how you can organize data. There are various ways how you can shape and manage data. And so we will talk in very broad strokes about these backgrounds. Then we will talk about sampling from populations in order to gain insights into dynamics in your sample and extrapolate these to the dynamics in your population. And we will talk about design of experiments. So today we're going to have a quick introduction to the course. We have an introduction and comparison of R and Excel. So this is where this little spreadsheet comes in handy that I have shared on Canvas. We will talk about the syllabus and the expectations from my end. And if there are expectations from your end, I hope to learn from them on the discussion board and also in an interactive kind of conversation today. Then we will talk a little bit about material. We will talk about identification of data types, the creation and interpretation of tables and graphs. So this is really kind of the objectives we have to what to learn. And we'll talk about all of this in the context of design of experiments, data, and sampling. So, but let's first go back to the course. So let's really talk about the syllabus. Let's talk about the expectations of this course. And so the course really aims to explain to you the role of probabilistic models, of inferential statistics and descriptive statistics. So essentially that already gives you kind of an overview of what statistics actually entails. So it describes data, and it allows you, by building probabilistic models and various other model types, to draw inferences and to understand dynamics and differences within populations. We will talk about the design of observational studies and experiments, and to also focus on inference. From these analyses that you will be conducting and designing, we will infer insights that are basically coming from public health. And for this very reason, you will have the final project to complete. And the final project will essentially entail analyses from the ENHANCE study, which is a publicly available, governmentally conducted research study, where you actually get real research data, public health data. So this will be very exciting. It's usually a lot of fun. And I'm very much looking already forward to your ideas that you will have on this data. And lastly, one of the outcomes of this course is also that you know, and I mentioned this briefly before, that you know how to collaborate and how to coordinate the work of experimental scientists. So it's really, we live in a world of extreme specialization, and I strongly, strongly believe in that. Everything in our world is about collaboration. And this is also why those of you that will not do any data analyses ever again still will benefit from this course, because it will allow you to essentially understand the work and the workflow of statisticians, of clinical research coordinators, of experimental scientists. And you learn what each of these key persons and stakeholders essentially does, how he or she does what he or she does, and how you actually can interact with them, and how you can communicate and converse about their subject matter expertise. So this is why I believe this course is to some extent also good to build interfaces between different specializations. So for the purpose of coding and data analysis, we will need an MS Office installed. So this is a regular accessible Microsoft Office, preferably the Office 365. You can also use open source alternatives, like for example, a LibreOffice. That's perfectly fine that you install that and work with that. It should also be a possibility that you use the Office 365 that is provided you by Yeshiva University. That should also be possible. But then you would need to download the files and upload them again to Yeshiva, which is a little bit more involved, but I think it could be done. It is definitely doable. You will also need to install RBase and RStudio. These are two different softwares, and I have posted a video, and I've seen that some of you have already started and watched the video. So the video kind of outlines how to install the various components. So it's important that you distinguish between R which is the base R. This is the actual core engine of the software. And then RStudio, which is, so to say, the compiler that kind of takes R and runs R within the environment. And we will look into the various aspects of both softwares, and we will look at how to use them today. Good, then we have a textbook, which is, it is required that you have it at your disposition because it's a wonderful textbook. It's open source textbook, which is free of charge. And you can download it for free from OpenIntro. And it's just really, it's a very good textbook. It allows for access to data files. It allows to access to codes. And so it's a very good resource.
Professor?
Yes, man. Yes.
Actually, this book is not being able to load. I've been trying to download it since yesterday. It's not been getting downloaded.
That's interesting.
The link is not working, to be honest.
The link is not working. Okay.
Yeah.
Let me make a note. I'll make sure to find the right link. So maybe the link has broken and they have changed and moved it. I'll have a look at it. Thanks for letting me know.
Okay.
Any other questions so far? Okay, so the other additional readings are more on the optional side. So these are also very good books. So they're very valuable, didactically designed books. But I do nevertheless prefer the OpenIntro and really suggest you get the OpenIntro. And I will get the link. Good, as for the criteria, so there's quite a few things to do. But they're overall, they're not really complicated, right? If you follow along, you're going to be perfectly fine. So we will be doing, with most of our lectures, we will be doing what is called here a practice lab. So a practice lab is essentially nothing else but a lab where we're coding together. So the idea of the class is we're going to do lecture for the first 45 minutes. And then the second half of the course of the class, we're gonna do some coding, where we essentially look into various questions and research questions and exercises, and we will code this together. And at the end of that class, you complete the exercise, and you upload the final output. And I will show you what that means. And this output is then essentially the objective of this assignment. And you will get with each practice lab, you're gonna get 10 points, coming to a total of 100 points. Then there are 3 graded labs. So the graded labs are a little bit more involved. So these are essentially, they come during the course of the class. And these are essentially those where you have to work on yourself. So these are autonomously to be completed, a little bit more involved. It will take you a little bit more time. See, there's some kind of homework, but it essentially is also, it will be, you will have the code available from the practice labs. It's just some more integrated, integral kind of more comprehensive analysis to do and assignment to do. So basically, but you have the codes available. Then part of it will also be the data camp. Data camp essentially is a wonderful platform. It's an educational platform for which I have sent out a link. Have you received that link? Yeah. Have you been able to register? Has that all worked out? Perfect. If there are any problems, just let me know, please. Hi, Aria. Oh, yeah. So if there are any problems with data camp, let me know. But yeah, so there's an introductory R course and an intermediate R course, which are essentially worthwhile 100 points. Okay, then we have the discussion board. On the discussion board, you basically have each week, you will have one video that is being published. You can essentially watch these videos for the period of 1 week, and you're being expected to comment on this video. to make, so some videos have some form of specific questions. Some other videos, I just want you to comment your thought and give your general thoughts on things. And so they are really cool videos. So the first week, for example, is one on the creator of spreadsheet technology. So the first guy who actually came up with the idea to create a spreadsheet, which is a genius, an absolute genius idea, because imagine having to do what you're doing right now in Excel, having to do that on a sheet of paper with pen and pencil, or with a pencil. It would be an absolute disaster. And like I can only imagine, like the physiologists in the 20th century, how they had to do their analysis with pen and paper. It must have been really, really tough. So I think this is a very brilliant idea and really a game changer for all disciplines to essentially come up with an idea like that and program this and make this generally accessible, right? Essentially, this was something, they didn't get rich with that. They made it publicly accessible. And then Bill Gates came on, took it for the creation of MS Excel. Then Apple had a different version. So it was publicly accessible as a patent for the common good. And basically then it became commercialized. And now, well, Excel is obviously the market leader, but now there are various different approaches up there. So yeah, and the comment on that essentially should be reasonable, rational, logically, should make sense in the context of the video, should make sense in the context of the question. And it's a fun exercise. So I have a couple of really good videos. I hope you're gonna like them as well. So there's some on artificial intelligence, there's some on driverless cars. So provocative kind of, interesting kind of topics. Then we're gonna do 3 quizzes. You're not gonna like the quizzes, but it's a fun little thing to do. It's 150 points. It's not gonna break the bank if you don't do that well on the quizzes, but yeah, so I just wanna make sure that you're keeping pace with the material. So it's just a little trick. And the heavyweight is really the final project. And this is really what it all comes down to. So this final project, and this is really what matters the most in this course. And I think this is also what's most fun about this course. So think of it that way. We're gonna learn coding over the period of the entire semester. And at the end of the semester, you are meant to have your own analysis conducted on an enhanced data set with up to 10,000 participants with real life data, actually lab values, actual blood pressures, actual weights, you name it. There are all kinds of data in that data set. And you're being asked to go through PubMed, which is the National Library of Medicine, and to go through population health studies, go through the enhanced studies that have been published already, look up some ideas you may be inclined to look at, and develop your own research hypotheses. And then dig into this data set and try to confirm or refute whatever the authors have done. So it's a fun exercise, and it's really fascinating what ideas your predecessors have come up with. Posted from Josh Lankin, some work, and I'm looking forward to see your ideas. So essentially the final project structures here in 4 different steps and phases. So the first one is essentially the creation of a first draft, which is essentially the idea, some references, some basic write-up, what things you would consider in the context of this analysis, what you think will be important. At the same time, we have to an analysis plan. And this is something that is very close to my heart. So this is something so I work for a think tank of analysis provider, and I'm in a supervisory role. And I have really religiously followed the strategy to have an analysis plan accompanying every analysis that is being done, just for the sake of having a document that documents what had been done, and B, having a document in place that allows the actual researcher to communicate with the statistician in an efficient manner. It's just much more efficient to actually have this in one document, have this master document being sent back and forth, and not have it in the analysis idea in scattered in 20 different emails. It's just, it can be really excessive when you have a group of prolific researchers trying to pursue a research question, and you as the statistician, you're trying to follow 20 different people, and they're throwing at you 10 emails a day. 10 multiplied by 20 is 200 emails. You're scouting yourself through 200 emails, trying to follow the train of thought of the group, which is not your subject matter expertise, because you're a statistician and you're not, I don't know, a nephrologist, or you're not a physician, or you're not a physiologist. So it's not your real expertise. You know a little bit about it and you know enough to keep pace with the conversation, but it's just much more efficient to have this in one document, have one person who is a subject matter expert maintain this document. And the analysis plan here means to teach you how to put such a document together and how to maintain it. Thirdly, then there's the final report that essentially should resemble, to some extent, an actual research paper. So it should have an introduction, it should have methods. We outline the methods that you have used. It should have results, and it should have a discussion. I don't want it properly discussed. I don't want every aspect of it discussed, but I want to see that you have put some thought into what you have analyzed. And then lastly, a presentation, an in-class presentation. And that's the fun lesson, because that's when I'm not speaking. That's when I'm just coming up with mean questions when you're presenting. And so this is when you're gonna be presenting to me what you did. So that's the last class in the semester. And all of this is worth 250 points, and it's really the mainstay of the course. Any question on this? It's a good overview, right? So essentially, so we have practice labs, so here's the narrative of that. Forget the earn 1,000 experience points. We're gonna jump right into the introduction of R with the graded lab. Yes, graded labs, as well as the practice labs, they're always, so we're gonna have the class on Thursday. Oh, I gotta rethink that. Let's do Wednesday. Okay, so I have to change that. So now we have Thursday. We used to have Mondays. So Mondays, then it was good to have like the time frame until the following Sunday. So I don't want you to stress out over it too much. I give you ample time to complete practice labs, graded labs. So we have the class on Thursdays, and we're gonna have time until the following Wednesday to essentially complete practice labs and graded labs. Good. By the way, which brings me to the next point. I am actually traveling next week, and the next class will also be remote. I think I have noted it on the syllabus, but I will be out of the country, and I unfortunately have to teach remotely. Okay, so quite some time will pass until we're actually back. And yes.
I'm sorry. I just need to ask, like, all our discussion gradings, like whatever assignment you gave us, it's due on Wednesday?
Yes.
All right. So for the discussion,
unless stated otherwise. So practice lab and graded lab will be due on Wednesday.
And what about the discussion post?
The discussion post is going to be from Sunday to Sunday. So it accompanies the week. So it's a week-wise discussion point. Yep. All right. Good. Any other questions? Yeah. Okay, fun project. Okay, so that's me, as said, physician scientist with focus on epi and biostats. I do research in chronic kidney disease. I work for think tank of a dialysis provider. Dialysis is a technological process replacing the kidney function in patients that have had kidney failure. And this is a highly technological process, but it's also a life-saving, life-sustaining process. But unfortunately resulting in very poor outcomes. So just as a comparison, the dialysis population had essentially with COVID, because they're virtually immunocompromised, they have a case fatality rate that was extremely high. It was in the general population, it was around 1% to 3%, depending on the region you looked at. In dialysis patients, it was up to 15 to 20%. So also a dialysis patient by the time point they get on dialysis, they actually have a 5-year survival rate that is comparable to some cancer types. So it's a very dire outcome, and there's a lot of research needed for this population to improve the outcomes. And this is the epidemiological research we are conducting. So I'm to some extent acting as a renal epidemiologist, so to say. And this is only part of my work, but yeah, it's basically very big data inclined, and we are collecting data. So the mother company essentially is dialyzing close to 200,000 patients in the US, and we get for each individual, for each patient, we get 156 treatments a year, and for each treatment we get somewhere in the realm of 400 to 500 parameters, and repeatedly throughout the treatment. So we have multidimensional big data for our dialysis patients, and we do a lot of prediction models and artificial intelligence in this data. So this is one of the examples where big data essentially makes a difference, right? So you have big data, and reading dynamics in big data allows for you to understand risk factors, allows you to understand how can you improve their outcomes, and which brings us also to one aspect that is actually super important when it comes to data analytics. So in epidemiology, you can do a lot of analysis, you can predict outcomes, you can find risk factors, but what you cannot do, you cannot establish causality. So you cannot say, okay, this risk factor has this outcome and causes this outcome with certainty. You can kind of establish some form of certainty about causality, but you cannot with certainty establish causality. That can only be done with experimental research, notably randomized controlled trials. And this is what we will be talking later when we come to the topic of design of experiments. You can only, when you minimize confounding, which is done by randomization, with certainty establish causality. No other research method can do that. Good. So this was a little excursion in the realm of chronic kidney disease. So I have done research in various capacities in clinical research and now moved over to epidemiological research entirely. I'm also an editor of, in the meanwhile, 4 journals. I'm peer reviewing for several journals, and I'm just quite involved in the subject matter of dialysis and chronic kidney disease. And this is really where my expertise lies. As said, I'm teaching out of pure passion, and this was really something I embraced, facilitated by my academic advisor, who I also owe a big thank you for allowing me to use his slides. So these are slides of Professor Levi Waldron from CUNY School of Public Health, who kindly has allowed me to use his slides. And he facilitated really my start into the academic world and to embrace teaching. And I'm doing that really with a lot of passion and enthusiasm. And I'm teaching this semester, I'm teaching 3 classes. I teach an undergraduate class and I teach a class at CUNY. And I have the pleasure to work with you guys this semester. So it's really a lot of fun. Okay, but now let's dig into some statistics. Let's dig into some of the material. So we have spent now 30 minutes chatting about the course. Let's get into some of the material. So what is statistics? So we have 3 major components of statistics. And the third one, which is here listed as the first one, is essentially a component that is somewhat underappreciated, I have to say, and most textbooks will only list description and inference, so the last 2. So, but the design and planning, how to obtain and how to collect data, is actually something that is of greatest importance whenever you design a research study. And this is clearly something where you should always consult with a statistician. And believe it or not, it's sometimes not done. And this sometimes has really, it backfires. So it's always important to keep the brains that actually will, in essence, try to make sense out of your data at the table, and make sure to listen to them and make sure to ask them for their opinion. It's like, how often should we measure this? How often will you have this assessment being done that your probabilistic model that you want to throw at my data will really converge and produce converges when it actually, when the model actually is able to make an accurate precision with accurate certainty to actually produce an output. So the technical term is converging. And so how many of these data points do you need? How often do you have to have this assessment? What's the time frame in between? Other questions, sample sizes. When you design research, you will need to know how many patients do I need to study to be able to make conclusions with sufficient certainty to essentially make sure that I can say, okay, so my blood pressure medication actually makes sense, or my, I don't know, my blood pressure measurement actually has a significant effect on my outcome. Whatever intervention you're studying, you need to know how many people do I need to study to have sufficient statistical power to make solid conclusions. So this is the design. Then we have description. And when you have data, you will try to make sense of your data. And you make sense of your data in two different ways. You firstly will describe it because you need to get a feel for your data. You need to understand, how does that data look like? How often was it measured? How does it distribute? And we will learn what that all means, what I'm saying right now. But you will need to describe it. And there are various ways out there how you can describe data. And this description and this summarization is one of the big tasks of statistics. And it's actually every analysis, every analytic effort has to start with a thorough description of your data. That includes the building of histograms, the building of summary statistics, central tendency and variability equally, and to kind of make sure that you understand what the data looks like. And thirdly, and this is where it's getting interesting. So now we're coming in the realm of hypothesis testing. So you want to draw inference from your data. You want to understand, you want to do comparison between groups. You want to build models that predict dynamics within your populations or your sample. And you want to be able to make decisions and predictions that take into account the also uncertainty, incomplete information, and allow for you to extrapolate your insights in your sample population to the overall population. And this is really what inference is. You want to describe dynamics and differences, and you want to extrapolate it to the larger population. And this has been done for years. And I encourage you to really look at these PDFs because statistics are very old. Dynamics have been found in various aspects. And it's really interesting to look. So here, for example, is Reverend Thomas Bayes, who has, so now this is very small, I'm well aware, but I'm just pointing this out. There are really people in there that have made a difference. The Bayes theorem is one of the basic theorems used in mathematics and statistics, which allows for the quantification of conditional probability. Then we have the, who of you has seen the movie Imitation Game? Alan Turing, who well, I highly recommend the movie. Alan Turing from the UK, great mathematician, has deciphered Enigma, the German coding machine that was used during Second World War. And they basically had like the first computer ever designed. And back then, this filled a room. This filled an entire room that machine designed. And then in the 50s and 60s, they built the first computers, quote unquote. Particularly IBM was like leading on that. They had like, that filled like entire floors, was like a computer. Things that are right now done with your watch. So they did calculations that essentially have been for us ridiculously small. And it took them large efforts to actually make that happen. Nowadays, everything is smaller, smaller, smaller. And the things that are currently being calculated by the smallest of all devices is just incredible what technology-wise has happened now over the years and decades. And just in the last decades, it's like we have this exponential growth of technology and innovation. It's fantastic. We just can hold our breath and wait what's going to come in the next years. Okay, so but this is the timeline of statistics, and it's funny. So when you go on the website, you actually can go through each of these examples, and it's quite nice. Also, there's John Snow. There's the first epidemiologist who actually, with statistical methods, fairly simple statistical methods, was really the first identifying the source of a cholera epidemic in London. It's a fabulous story if you're interested in the backgrounds of epidemiology. So it has really a long history of improving people's lives. Okay, so but now let's stick with the basics, right? So we're coming back to definitions. So as I said, you do statistics in samples. Why are you doing statistics in samples? Because you don't have access to the population. A population can essentially be every group of interest. It can be all people on the planet. It can be American adults. It can be residents of New York. Whatever population you're looking at, it's very unlikely that you will be able to quantify each single one of them. It's hard to study every American, right? It's gonna be quite an effort, except for when you do a census. But even then, with a census, you can't go, in the context of your census, you can't go to somebody's house and measure blood pressure. You measure, I don't know, 450 million blood pressures. It's just not feasible. You can get some information with the census, but you can never get all the information. But basically, for this reason, you need samples. So populations is the entire group, whereas a sample is a subset of this group. And so you do subsets, you do surveys in the subsets, and you try to quantify whatever you want to quantify for your population in subsets that kind of will reflect dynamics in your population. So this is why the choice of sample is extremely, extremely important. And we will have a separate sampling session where we talk about sampling only. And it's art. Like sampling right is super important because when you think about it, like most research studies, they're convenient samples. What we say, we call it a convenient sample because a sample is not easily accessible, right? You need to find a subset of your population that actually is in any way interested to do research with you. Not that easy, particularly if you don't have funding. If you give them money, then obviously. But then also you run into ethical problems because you're not allowed to pay them too much money. So it's a tricky business. So for that very reason, you need a sample that basically will participate in your research, which is hard to find. So now you end up basically choosing a sample that is easily accessible. What's the problem? The problem is that sample is a quote unquote convenient sample, but the convenient sample comes at a price because there's a reason why they're a convenient sample. So like, imagine you're doing a survey and you say, you ask yourself, okay, so you do a survey on, I don't know, some health outcome. You are basically placing yourself somewhere where you think you will be able to find a lot of interested people. And you go in a mall. And you go in a mall and you place yourself at the mall and then you ask everybody who walks by about their health behavior. And you quantify that for 100 people. And then at one point you turn around and you see right next to you, you see a McDonald's. So there's a problem, right? There are factors in your determination that you need to consider. And you need to understand what makes this convenience sample potentially what we call biased, which means they're to some extent influenced with factors that we haven't taken into account that may make the dynamics in our sample different than those in the general population. So it's very tricky, and it's a whole body of own research, essentially research within the research. It's also I've studied that quite a bit because I am associate editor of the journal Trials, and Trials is basically focusing on research methods and aspects like sampling and recruitment into randomized controlled trials only. So this is really, there's a lot of research, and there are journals like Trials is a journal that is focused only on that aspect, on how to design research. So it's of great importance, and it needs to be kept in mind. Okay, so we have a sample is a subset of a group of interests of a population, and a survey of the entire group is called a census. So we do the census of the US population, and we get a sample of not the entire group, but we get a large part of the population. Every single observation in your records is called one record. So one entry is one record, but your entire database is then built up with multiple records for each individual. Descriptive statistics essentially have been conducted since a long time. This, for example, is here public health data, so it's the conquest of pestilence in New York City. And this is also where epidemiology in London, this cholera outbreak that I mentioned, John Snow, he did graphs like that, where he quantified what is called here the death rate. So death rates, you can have death rates or incidence rates. So incidence would be the incidence of a disease of any kind, standardized for a certain fraction of the population. So you basically have deaths per 1,000 population, gives you a death rate per 1,000 people in the population over the same observation period. By that, you standardize it, and you see over time, you see here was a cholera outbreak, and the incidence or the death rate spikes. Then it goes down again, and then it comes up again. Here's the cholera again. And we have yellow fever in New York City, right? So essentially you have here spikes that are reflective of diseases that happens in your city. So this is descriptive statistics. This is one form of descriptive statistics. There are obviously different forms of descriptive statistics, but that's one of them. And for epidemiology, this is very important. It's called a so-called time series graph. So you basically have on the y-axis here, you have some metric, and that reflects any metric, any parameter or variable of interest over time. And you basically have on the x-axis, you follow it with a time metric, which is here the years. Then we have inferential statistics. Inferential statistics are essentially also descriptive statistics, or can be descriptive statistics, but they produce results that allow for inferring some dynamics or comparisons. So here, for example, we have okay, I gotta update this one. The Trump approval rating by multiple polls. And we essentially what we have here, and this is where we're running into inference, because we have here what is called a margin of error. And the margin of error will essentially reflect the estimate from your sample, and then also the uncertainty around your estimate, allowing for the comparison in statistical terms. So essentially, if your margins of errors do not overlap, this means that there's a significant difference, what is labeled a significant difference between both curves. And again, this is a time series. And by plotting the uncertainty and taking into account the uncertainty, you're essentially taking into account that there may have been significant differences over time. So this is inference. So you want to draw inferences about an entire population based on your samples. How great is the uncertainty? And then the next research based on that is not only how great is the uncertainty, because that will determine whether there are significant differences. And then you also want to know what actually causes this uncertainty. And this is where sampling, again, is a very, very important conversation to have in this context. All right, types of data. So we essentially were looking at 4 different types of data. We're looking at nominal data, which is binary, dichotomous, or categorical data. Then we have ordinal data, which is ordered data or ranked data. And then we have discrete data, which is either integer data or count data. And lastly, we have continuous data. So there are various slightly different definitions. So you can, for example, you can also stratify continuous data into interval data and ratio data, where ratio has a meaningful 0. It's like, yeah, let's stick with that for now. When we look at nominal data, it would be a binary data, and this becomes really important when we will talk about logistic regression. So I hopefully we will have time to talk about logistic regression. So you will, with every outcome prediction, you have a 0 and 1 outcome. So when you think about death, for example, as the most terrible outcome, obviously, but essentially you need to dichotomize that outcome. So if you say somebody did not die over the period of 2 years, you use a 0 to essentially say this individual did not die. If somebody died, you give it a 1. So you get a binary dichotomous outcome. This is a nominal data point. Then you have categorical data, which is, for example, blood types, where you say 0, 1, 3, and 4 is reflecting A, B, or 0. And these are only nominally numbers. And it's important to keep in mind that these cannot be used in numerical terms. So both binary and dichotomous and categorically are not allowed to be used to sum up or in any way used arithmetically, because they essentially are not arithmetic data for obvious reasons, right? If you just count them, like you can do with 0 and 1, for example, you can count them and you get all that had a treatment or all that are dead, but they're not to be used in any numeric form. So you can't make an average between them. It's just nonsensical. Then we have ordinal data, which is, for example, data on a performance scale, where you have fully active, can do light work, no work, ambulatory, disabled. So again, this is not strictly numerical data. It cannot be used for arithmetic approaches. It is only numbered for the purpose of ordering. Magnitude is unimportant. So you can make this 0, 100, 200, 300, 400. It's just absolutely irrelevant how you define those magnitudes. Problem with that is, so you will have some data like that available when it comes to physical activity, for example. In the enhanced data, you will have physical activity. This, for example, is classically ordinal data. Yes, absolutely. Yeah. Hi, Jutta.
Hi. So is the difference between ordinal and categorical and nominal, is the difference just that you have like a spectrum and it's like increasing?
Correct. So it's essentially they are the same kind of data. They're categorical data, but the ordinal data does have a sequential order. So this is really the difference. Very good point. Thank you. Order is important, magnitude is unimportant. Rank data is an important type of ordinal data, and So even ranking is a little bit more specific than performance scaling, because ranking essentially gives you within a data set, it gives you a rank within a group of data, right? For example, you have non-parametric tests that only compare ranks and not the actual value. But we'll talk about that later. So rank data is a special type of data. Also ordinal data. When you look at this, these are the number of deaths for leading causes of deaths in 2010. So we have heart disease as number 1, cancer number 2, chronic lower respiratory disease 3, stroke 4, accidents 5. The ordinal data is 1, 2, 3, 4, 5. This is not ordinal data because this is discrete data. So the ranking is ordinal data. This is discrete data. These are counts because these are the number of people that died from these respective causes. Important to distinguish because if you need to identify it, you need to know which one is which one. So again, here you have these cases. You have here the count data, and then you have here the rate, which essentially is a typical way of depicting data in epidemiology. This is standardized. There's fluctuations in the order and order. Discreteness becomes important. Magnitude matters. Arithmetic applies. So you can, with these arithmetics, you can actually do arithmetic operations, and you can actually hi Rana. You can actually do computations with your data points and with your discrete data that you have at your disposition. And lastly, we're going to talk about continuous data. And continuous data can be anything that you essentially measure. So this can be time, can be weight, can be length, can be mass. Various other examples in my world, it would be blood pressures, lipid levels, you name it. So there are many different types of data that you can measure. And characteristic is that there's either there's a bound or there's non-bound. In most cases, there's some form of a bound, particularly when it comes to physiological data. Magnitude matters. Yes, Aisa?
What does it mean for it to be bound?
Is what?
What does it mean for it to be bounded?
It doesn't have to be bounded. It can be from 0 to infinity, and it doesn't have to be bounded. But in many cases, it is. It's also you again with continuous data. You distinguish between interval data, which is equally spaced and also can take on negative values, or ratio data that essentially has a meaningful 0. So temperature is a good example, for example, for interval data. So that also can go negative, but again, is in many cases then bounded, in others not, but it also can go negative. But when you count something, it's essentially, it becomes discrete data. But then also if you have a certain kind of meaningful 0, where time is a good example, for example, because you don't have negative time, you're looking at quote unquote ratio data. So it's not always bounded. In many cases, it is. Answers your question?
Okay. Yes, thank you.
All right, great. Okay, the summarization of data is very, very important. And you are supposed to be doing it for every data set that you analyze. So there are various approaches to summarization that you can use. You can do this for every data type that you essentially are interested in. And it's of greatest importance because you identify outliers, you understand the distribution. So there are various reasons why you would do summarization. And you also need this to essentially come to the next steps of analysis, where you essentially would need knowledge that you have from summarization in order to proceed with your analysis. So nominal data ordinal data, discrete data, and continuous data. Any further questions on these data types? No? All right, good. Pie charts. Okay, so how can you summarize data? You can summarize data essentially in various ways. If you look into binary and categorical data, one way to do that is to use a pie chart, which is strongly discouraged from actually being used. Firstly, because it's, and this is kind of a funny example of how you can actually misdo a pie chart. And also a pie chart is an utterly uninformative graph. It's just, it doesn't contain any information, and it's really something that is more for lay magazines that essentially do not mean to convey much information. In scientific journals, it's highly discouraged to have pie charts. So I don't think I've ever even tried to submit one. This is, but again, there are some people like pie charts. I despise them. And I also dislike three-dimensional graphs. You have in Excel, you have like the possibility to do like three-dimensional graphs. Again, utterly uninformative. It's like if I have 3 bars stacked up next to each other, it's like you cannot see the result of each of these bars. So it blurs the insight and the understanding of whatever data you mean to present. So a contour plot is a much more elegant way, but that's more of a topographical map, right? If you want to really do three-dimensional depictions, I highly encourage contour plots. Okay, pie charts. Okay, so we don't do pie charts. What we can do and what is nice to depict categorical data is the computation of frequency tables. And we will do frequency tables, particularly when we come to the only non-parametric test that we will be discussing, which is the so-called chi-squared test. These contingency tables essentially give you a grid where you have 2 dimensions coming together. So I'll show you in a second what that means. So you essentially have in the respective cells where these 2 variables come together, you have the count where both of these conditions apply. So thinking this through now, so you are looking now at single, nominal, or ordinal variables. You have treatment or control. So this is the design of a clinical trial. So you have a control group and you have a treatment group. You will assign them in a 50-50 ratio, and you will have half in each group. You have now as an outcome, you have a severity of a certain condition. In this case, the example used is pain. So you have mild, moderate, and severe pain. You have mild pain in 20 cases, moderate in 30 cases, severe in 50 cases. And now we're bringing the frequency table on the next level, and we're adding a new dimension, and we're basically adding now treatment and control on the columns and mild, moderate, and severe on the rows. So the marginal totals that you see here are adding up to 100, right? They have to. Same here. But you have within your contingency tables, you see differences between treatment and control within the respective pain severity levels. So this being said, you can already kind of guess that this can allow you to draw inferences in your data and in the dynamics within your data, right? So you have a good way to essentially compare treatment and control outcomes. And yeah, marginal totals, marginal probabilities. With the marginal totals, you can now calculate the marginal probabilities by essentially dividing the numerator of 50 by the denominator of 50 plus 50 is 100. So essentially, and the same you can do here with the marginal totals and probabilities for the respective rows, which will allow for you to also calculate risk ratios. Because within of these groups, you actually can calculate a risk for each of these treatment groups. But we'll talk about this later when we come to applied probabilities in medicine. Okay, you can equally display your categorical data also in bar charts. So you can say, okay, so this is a rather non-informative bar chart, but essentially you can show this equally as a bar chart where the bar on the y-axis actually reflects the number of cases within each group. You can stack this. Again, I'm leaning towards labeling this rather an uninformative graph, where you have a stacked bar chart with these pain severities labeled inside. So again, it's difficult to compare, for example, this one and this one because it's not on the same scale, but again, there are various other ways. So I prefer bar chart right next to each other because it's easier to create if you have treatment, yes, no, and one pain severity, treatment, yes, no, another pain severity group, and then the same for the third group, makes it just easier to grade. But again, that's just me. So there are various ways how people approach data, and there are differences between preferences, statisticians, educations, you name it. So people do things differently. Okay, so you have frequency tables. You can use that for discrete and continuous data. So this is count data with appropriate bins, and you basically discretize and further discretize. And you can do that for nominal and ordinal data. And this brings us essentially now to, so here we've seen that. Smaller bits is a bigger table. And this brings us now to the histogram. So the histogram is essentially what you will use to define these pain severity groups. So if you want to find out what is a good grouping, you need to understand your data and you need to map your data out. And the mapping of data is being done with histograms. So essentially what you see here, you have the pain severity on the x-axis, and you essentially have those binned and the so-called bins, which basically builds these bar graphs, where you have on the y-axis the depiction of the frequency, where the frequency actually reflects the survey that was conducted in that participant. So each of these entries, each of these points of frequency is one participant that has given one insight or has given one response. So by discretizing this now in different bin sizes, changing the bin width gives you different categories. It gives you different counts within each category. So you can go and change these bin sizes until you finally come to bin sizes that do kind of reflect a response that kind of creates differences between these groups. So this is how they came up with mild, moderate, and severe. So they mapped out the data. They see a somewhat normal distribution with the bin sizes they chose first, and then they kind of split it in equal parts. And that's how you define on groups. But to do this, you need to map data out, and you need to see data, and you need to graph data out that you essentially understand how your data distributes. And we will talk about frequency distribution in one of the later classes. But this is essentially the basis of looking at data and understanding data and characterizing data. So in addition to that, you can also make frequency polygons, which is essentially a depiction of data density, which is essentially nothing else but overlaying the bars with an actual frequency polygon, which is essentially a function that follows the counts within each bin. So this can be done with a function in that format, or this can be done with a smoothed function like this, that essentially is a smooth probability density that allows you to more obviously see the shape and how the data actually presents. So when looking at density, so these density plots are essentially how you see the density, how you see distribution, frequency distribution depicted in many cases. And so this is, for example, what one would call a normal distribution, where you essentially see normally distributed data. When you want to depict that, you can do this in various ways. One of the more elegant ways to depict data is a so-called box plot. A box plot is essentially a depiction of data where you have several things depicted. So you have here in the middle, you have the thick bar is the so-called median, whereas you have on Q1 and Q3, you have, so this is the middle. So you have every respondent. So you have 100 people. Where the median is, this is where 50 is. So you have to the left of the median, you have 50 individuals, and to the right of the median, you have another 50 individuals. Between that thick bar and this bar, you have 25% of your individuals. So this is 25 people, is right in here, in that box. 25 people is in here between Q2 and Q3. So this is the so-called 25th, 50th, and 75th percentile. And then you have median, and then you have the interquartile range, which is here between this one and this bar. So everything in that box is the so-called IQR, or interquartile range. And then you have here these whiskers. So it's a box and whisker plot. The whiskers essentially are Q3 plus 1.5 times the IQR. So this is, it follows a principle, but it essentially is, it's every box plot on the planet is going to show the same formula. And then you have everything exceeding those whiskers. It's going to depict it as a so-called outlier. So then you want to show data as a so-called one-dimensional scatter plot or a strip chart. Except for some survival analysis, I have never really showed a strip chart like that. You can do it, why not? But it's not a very common way of showing data. Then you have the mashup combinations, and this is where I'm going now on my rant with SAS. No, I'm not going to really rant, but I am a very passionate R user, and I like R. So I'm just not a fan of SAS. I have attended 4 classes during my master's where they have tortured me with SAS. I hate the syntax. I hate this function-oriented kind of programming. It's the worst. It's even worse than SPSS. And so I'm just genuinely enjoying R, and this is just easier, more beautiful, graphs are nicer. And one typical thing with every SAS analysis that you will see is exactly that. So you essentially have these graphs, and there's like literally every analysis on the planet on this graph. And it's just, it looks busy, it's too much information, it's not easily customizable. It's just, for my taste, it's too busy. But again, SAS has, and then this is now me, okay, on a less humoristic note. So I really don't like SAS. That's a fact. But that doesn't mean SAS is not it's a very potent, very powerful software, and it is very good for big data. It is very fast processing big data. It has great tools, and it's and it justifies to some extent a smaller fraction of the price it actually costs. Let's put it that way. So it's terribly expensive, and I personally I just enjoyed R more. Okay, so this is SAS. These are the mashup combinations that SAS can produce if you tell it to. Then you have what else we got? Okay, summarization of data. So we have spoken about nominal and ordinal data. We've talked about frequency tables, which we can do, and plots like bar charts. And then we have talked about discrete and continuous data with the discretization as frequency tables and plots, histograms, box plots, and frequency polygons. Then we have, without further discretization, we have the scatter plot or strip charts. And scatter plot, I'm not sure we actually have seen a scatter plot. We're missing a scatter plot. Inside the scatter plot. So a scatter plot is essentially where you have a raw data point, where you have y-axis and x-axis shows you an exactly matching data point on one bar, on both axes. We will see plenty of those, so you will definitely see scatter plots, but it essentially shows you the entire scatter of data. Good. So this was all for today. And it took a little longer than expected. So we are essentially, so we have 16 more minutes. Okay, any questions? Or was that, it was kind of a lot of information, right? But no, I hope it wasn't, I hope it wasn't too much new. It will even get more information, but it's like, it's very important information to start with, and it gives a good start into the topic. And you will see everything is going to build up on each other, and then it becomes very, very clear. Okay, so now we have now data. Let me zoom into this for a bit. We have here data of 4 individuals, Teresa, Sarah, John, and Nicole, who are essentially earning, I don't know, by selling newspapers, they're earning a certain kind of income. They're earning over the period of 4 years, and they're earning at different ages. So now you have various functions in Excel, and I don't know how savvy you are in Excel and how knowledgeable you are with Excel and basic functions. So there are various things that you can do in Excel. So if you, for example, want to quantify, who of you has a really good grasp on Excel? One. Oh, okay. Okay.
Not excellent, but
okay. Okay, but you're somewhat confident. Okay, good. So essentially, what you will be doing in Excel, I just want to walk 5 minutes through Excel, a little bit basic functions. You will do functions by creating an equal sign, and doing that equal sign will essentially for you to allow to add any form of arithmetic exercise or a function. So if you do equal, so each of these cells does have a certain location. So if I go on column D and row 2, I get D2. D2 will be recognized by Excel. If I want the next entry for Teresa, this would be D6. So I can do plus D6, okay? And that's fairly easy. Plus D10 will give me the next entry for Teresa. Now I'm adding this up and I get the sum of what Teresa has earned over the last 3 years. If I want to propagate this formula, and this is where it's getting important, and this is just really the most important thing in Excel, that you understand that. If you click now on the cell and on this, oops, and on, no. So if you click on this right corner here, you can pull this formula down. And this allows for you to not only shift the formula, but also shift the target cell. And this is important because by that, you essentially can propagate your formula for as many individuals you want to propagate. This plays a role because you essentially want to quantified for each cell and without having to type this each time around. So if you want to have now the sum for all in 2018, you do D2 to D5. Oops. D2 to D5 gives you now all for 2018, right? If you want now all for 2019, you would need to go again in the same spirit, go through the first entry of 2019 and propagate the same formula. It will shift the entire formula. If you want to lock your cells in, you can do so with the $sign. The $sign essentially will allow for you to lock that cell in. And this is important when you do some certain arithmetic functions, because if you're copying this now down, let's just copy one down, it will still use the same frame. So if you want this shift of the target cell not to happen, you need to lock the cells in with the $sign. Does that make sense? That's fairly simple and easy. It's, for example, if you want to do a calculation like this, you do count this, comma, this, comma, this. So this counts now the cells that you have given. So these are 3 cells, right? So if I'm propagating this down now, I can do so. So it will give me, again, all the counts for this. So if I want to do now, yeah. Okay, so this is how you, if you were to calculate now an average, you can do this by taking this divided by this. Alternatively, you can also use the average function, which you may know. There's a function for pretty much every arithmetic exercise that you can do. So we're just getting slow now. Okay. So this is the average function that essentially results in the same outcome. So it gives you the average, gives you the same. So, and now we're going to transition over to R. So we have 10 minutes. In 10 minutes, I'm going to walk you now through R. So what we're doing in R is essentially, it is comparable to what we have done in Excel. What's different is it is not graphically. So you're not literally, you're not clicking, you're writing it. If you look at our studio here, you have here on the left upper quadrant, you have the script. I would encourage you to please go on your desktop and create right now a folder which you call BTM6000. You create in that a folder, module 1. And now, and I just realized I didn't put that on Canvas. That was not good. Okay. I'm putting now a code on Canvas that you can download from Canvas. And this is coming in a second. Hold on a second. It's not smart to not post this. Coming up in a second. And greetings, assignments. Module 2, module 1. Let's this first into files. Archives. Sorry for the hiccup. 6,000 archives. Okay, so you have now in your canvas within the next 30 seconds, 10 seconds, you're gonna have now an R code. Okay. So if you go on your canvas now, you have here module 1 rcode.r. If you download this on your folder on the desktop, you can then upload it into R by just double clicking it. By double clicking it, it ends up here. Yeah. So once you did that, in the meanwhile, while you're doing that, and listen to me in the background. So you have on the left upper quadrant, you have now your code. This is the script. So this is where you're typing what you want R to run for you. On the left lower quadrant, you have the so-called console. The console is R. The console is your actual core engine. This is actually what you're running. On the right upper quadrant, you have your environment. In your environment, you have all the objects that you have loaded. What does that mean? If you're selecting now row 1 to 5 and you click on run, you will see that in your environment, you have now an object labeled df. df is the spreadsheet, the Excel spreadsheet that you have. That's all it is. And if you click on it, and there's a little tabularic symbol on the very right. So you have df, 12 observations of 4 variables. And on the very right, you have like tabular depiction. You see view df, and it opens up just like an Excel spreadsheet. You can't type in it yet, or still, but now you can access it. And what you can do now, you can address that thing. So if you write now in your console df, you're gonna get df. If you write df bracket, comma, 2, you get all entries in column 2. If with your brackets, and this is where data camp comes in handy, because data camp is going to teach you this repetitively and redundantly. You're going to practice this and you're going to get a really good hang on it. So essentially you have df, and if you want to have one specific column, row, or cell in df, you can specifically address this with a bracket, which is separated with a comma, and you have everything after the comma indicates the number of columns you want to count to the right. Everything before the comma, so this is 1, 2. df bracket, comma, 2 indicates column 2, so this is age. If you want to have age, you go df column 2. If you want to have the age of Teresa, that is the first one, you do df 1, 2. That's 28. So you give after the comma, you give it the column. Before the comma, you give it the cell, the row. If you do one comma, a column, 4, you do 1 to 4 as a row. Column 2, you get all the 4 ages of all 4 individuals. So that's how you address cells in R. That's how you get specific cells out. Okay? I'm deleting this now. If you get the first row in the data set, you get df, 1 and a comma, you get the first row. If you want all earnings, you take the 4th column. These are all the earnings. If you want df or the earnings, that's an alternative solution. You do df earning and you write it out. If you want to have all earnings by Sarah, you do df with df name double equal sign. Double equal sign becomes a condition where you do df name equals Sarah and the column after the comma equals earning. Yes. Hi, Isa. Yes.
Hi. So writing it out is just an alternative way of doing the same thing with the row, comma, column. Yes. Okay.
Correct. Yes. It's I usually it depends. It depends when you would do it. There are occasions where you would do it. There are situations where you would do it. Usually you wouldn't. But it's a longer story. It's a longer story why. So we're gonna get to iterative loops and then it becomes clearer. That's not. So Sarah earnings, so you can now take all the earnings in Sarah, and this is now the so-called pipe. This is basically stuffing now, whatever you want to stuff into a new object, you can create a new object. And this is now your earnings, Sarah earnings, which contains 3 numerical values, 110, 121, and 190, which is consistent with Sarah earnings.
Professor?
So this is, yes?
Actually, we have another class which starts at 7.
Oh, yeah. That's fine. No worries, no worries. Thanks for joining and see you next week.
Thank you.
Yeah. So that brings us actually to the end of this class. A good point, actually. Yeah, and you can use to pack things into new objects. You can sum up whatever objects you want to sum up. You can employ all criteria that you want to employ. You can look into years specifically. You can, with lengths, you get the lengths of entries. So these are all the functions that you do. Play around a little bit with that code, and I'll see you next week on Thursday. Have a nice evening.
Thank you, Professor. Take care.
Have a good weekend, Professor.
Thank you.